Alrighty, we are back. We're back, baby. Not a whole lot left to do for this week, if I'm honest. We have been talking most recently about indefinite integrals and the net change theorem. So I would like to take a look today at a handful of other problems associated with the net change theorem, make sure that we're very comfortable doing this sort of calculations. I can try to give you a little bit more perspective on absolute value functions and why integrating them works the way it does, although I'm not sure that's necessarily going to help you with the problem solving, and I don't want to get too lost in that quagmire. So that would leave a little bit of time maybe to introduce what we're going to move into next week, which is sort of a backwards version of the chain rule called U-substitution. Maybe the best way to begin would be with a call for questions, because it is actually fairly open. If there were any particular problems from the homework set that you wanted to see, I would be perfectly happy to take a look at those, and then we can work our way into a little bit of net change stuff. Oh, and initial value problems. That's right. We wanted to look at those. So let me go ahead and fire up the document camera. Can we go moving? This, of course, as always, is MAC 2311, section number 004, which is a Calc 1 class. And the date today, I believe, is the 8th of April. Today. We can do a little bit more with the net change theorem. I want to look at something called initial value problems, often abbreviated as IVPs. And for those of you who are going to go on to take a course in differential equations like MAC2311.004, IVPs are kind of a really good introduction. And then maybe we'll introduce the idea of U-sub. Which is
Did you still want to do that poll to see what's better for everyone to take the exam on?
Yes, absolutely. Thank you for reminding me. Let's go ahead and create a poll.
You said for like the 20th, it would be, if we took it on the 20th, we would do review for that for the final on the 22nd. But if we took it on the 22nd, we would do review for the upcoming exam on the 20th, if that was right.
Idea. Yeah, so if we want to save a day for reviewing for the final, that would be the 22nd. And that would mean we do exam 3 on the 20th. And then the other option here is to have the test on 4/22, the last day of class. With no dedicated review day for the final. All right. We have a decent sized quorum here, kind of, I guess as many people as I could hope. I'll go ahead and launch the poll. All right, so if you'd rather have the test on the 20th, that means the test will be sooner, right? Less time to prepare for exam 3, but a little bit more time dedicated to prepping for the final. If you want to have the exam on the 22nd, that would mean you have a little bit more time to prepare for exam 3, but no dedicated review day for the final. And with that, we've already got a majority. Supermajority. Okay, now with 8 out of 10 folks going for the exam on the 20th, that's when we're going to do it. I'll go ahead and end the poll. Results. So this means that exam will take place on the 20th. All right, and of course, this is the same way it always is. This will be during class. Proctored. Zoom and on a lock. So same procedure as for the previous tests. You will sign into the Zoom link on your phone, and then you will go through the normal on-a-lock stuff on your computer, and then the test will be in Canvas. The final is, by the way, also the same sort of format. It's just a slightly longer test, and it's weighted a little bit more towards the true, false, and multiple choice. Okay, so a slightly closer look at the net change theorem, I think is not inappropriate. Last time we were able to set up two problems, but we only solved one of them that actually involved a velocity function, which was not always positive. So I do want to follow through solving one of those slightly more complex problems. The other thing is maybe a little bit of a closer look at the absolute value function. So I'll try to keep this brief. Absolute value is way underrated. It's not something that we study nearly enough in pre-calculus, and given that pretty much all of calc itself, when you go to prove the sort of things that we've been doing throughout the semester, pretty much always involves inequalities with absolute values. So in case you've never seen it before, we all have an intuitive idea of what absolute value does, but the definition of the absolute value of x, right, we normally just think of this as make x positive, but how do you do that? Well, the answer is it's x if x is greater than or equal to 0. So if you're positive, or at least non-negative, the absolute value function leaves you alone. And it's the negative of x if x is strictly less than 0. So if you are negative, the absolute value function multiplies you by -1 to make you positive. And this generalizes if you have the absolute value of, I'm going to put v of t in here because that's the name of the function that we're most often working with. This would be good old v of t if v of t is greater than or equal to 0, and the negative of v of t if v of t is less than 0. And this is really why splitting up the integral the way we do is effective. All right, this is precisely the reason. So if v of t looks like, v of t looks like this, and maybe a is here, b is here, and I want to integrate the absolute value of v of t and the integral from a to b of the absolute value of v of t dt. If I mark this maybe as c, probably change over from positive to negative, this would be the integral from a to c of the absolute value of v of t dt plus the integral from c to b of the absolute value of v of t dt. And then from a to c, v of t is positive. So the absolute value of v of t is just v of t itself. And then from c to b, in this integral, the v of t function is negative. So the absolute value of v of t is actually negative v of t. So that's where that minus sign was coming from. We can annotate here. So on the interval a to c, the absolute value of t, the absolute value of v of t is just v of t. And on the interval c to b, the absolute value of v of t is negative v of t. So that's the reason splitting up the integrals the way we have been doing is effective. So that's the reason why, in order to integrate the absolute value function, you split up the integral according to where the function is positive and negative. And of course, you would do this for any function you're trying to integrate the absolute value of. There's nothing sacred about a velocity function here. It's just that this is the setting where we need it. Elsewhere in the universe of mathematics, integrals of absolute values of functions are kind of a big deal. And this is how they're handled in general.
Quick question. How come that when it's less than 0, it's still negative? Wouldn't the absolute value make it positive?
That's precisely what that negative does. So if you're already negative, the way I make you positive is by multiplying by another negative.
Right, okay.
That's the vibe. So like if we look up here, tack on an example.
Like how come on the graph it's not on the positive side?
All right, so let's do one thing at a time. So when we take the absolute value of a negative number, really what that absolute value is doing, don't think of it as stripping this negative away. Think of it as putting an extra negative out front, which makes the thing positive. That's the algebra idea. The graph I've drawn down here is not the graph of the absolute value. This is the graph y equals v of t. So the purpose of the graph here is just to illustrate where v is positive and where v is negative to explain the split. The graph of the absolute value of v of t would look we want to draw y equals absolute value of v of t. That will look different. We would have the same thing going on from 0 to c. But then actually it would be like this over here. So this would be c, b, a. Now you don't need to be able to picture the graph of the absolute value of v of t in order to do this stuff. So you haven't seen me draw the graph of the absolute value of any of these functions, but this would be, right? You're just going to take this piece and flip it up. So this really should be concave up like this when you flip. That's the idea. So I hesitate to show this, and I never show this on the first day we're doing this stuff because I think it kind of maybe especially this picture only makes it harder to understand. But if we focus our attention on this definition and the idea that you can split up the integral according to that property of definite integrals, right? I didn't do anything inside here. I'm still leaving this as the absolute value of v of t. But then in the first integral, the absolute value of v of t is just v of t. So that's just this guy. And in the second integral, the absolute value of v of t is negative v of t. Because between c and b, the function v of t is negative. So that's why this changes to a minus. If we want a slightly better picture of these sort of things, I can provide one. Look at something like this. Or maybe I'll restrict the domain like this. And then if I want to graph the absolute value of v of t, that's the blue, right? But like I said, you do not need that picture in your head. You don't need the bottom picture in your head to do this. You just need the top picture and the understanding that when the function is negative, to get rid of the absolute values, you just slap on an extra negative and the absolute values go away. But you do need to make the split. You need to integrate where the function is positive separately from where the function is negative. So we did set one of these up the other day, but we didn't get to follow through with it. Let's do one from start to finish. That is, a little on the complicated side. Something here. There's an example in the book that's not bad. Yeah, so we talked about this. Here we go. So particle moves along the line, so its velocity is this. It's down, v of t is t squared minus t minus 6. We've got two parts. Find the displacement from t equals 1 to 4. And we find the distance. T equals 1, 2. So for part A, we know what to do. We're just going to integrate from 1 to 4, v of t itself. That's how you get the displacement, which is the integral from 1 to 4 of t squared minus t minus 6 dt, which is 1/3 t cubed minus 1/2 t squared minus 6t evaluated from 4. The evaluation step here is going to be a little messy, so I'll give myself some space. This is, let's see, 4 cubed is 64, so that's 64/3 minus 4 squared is 16, so that's 16/2 minus 6 times 4. And we subtract what we get when we plug in 1, which is just going to be 1/3 minus 1/2 minus 6. 64/3 is not an integer, so I'll leave him be. 16/2 is 8. 6 times 4 is 24. -8 minus 24 is -32. And then over here, I'll have minus 1/3 plus 1/2 plus 6. So the 64/3 and minus 1/3, that is 63/3 minus 32 and positive 6. I can write that as a minus 26. Yep. And then I've got plus 1/2. 63/3, that is an integer, that is 21. So I've got 21 minus 26 plus 1/2, which is what? So that's going to be -5 plus 1/2. Which is -9/2. -4.5. And I think we're measuring distance here in meters. So this object overall went backwards. All right, spent some time going forward, sometimes going backwards. And because the displacement is negative, we know that the net change in position, right, which is the thing we're calculating, displacement is net change in position, is going to be negative. Any questions on the displacement calculation here?
I just have a quick question. It says for find distance from 1 to 9. Is that a 9 or a 4?
Oh, sorry, no, that's a 4. Yeah.
Okay, thank you.
Right. Then let's go ahead and do the distance calculation. We know that the distance would be the integral from 1 to 4 of the absolute value of v of t. And in order to know where to split this up, or even whether it's necessary to split it up, I need to figure out where v of t is positive and where v of t is negative. So if you factor this guy, right, t squared minus t minus 6, that's t minus 3 times t plus 2. We'll call this 1, 2. I'll call this 1, 2, 3. So I've got roots here. And then let's see, so so my vertex, I don't care too much about the height of the vertex. For the purposes of what we're doing, all I really care about is where the function is negative and where the function is positive. So if I want to find the distance from time t equals 1 to t equals 4, that means I'm looking for the area here. And I want to make sure that I measure both of these areas as positive. In the first integral we did, that gave us that negative 9/2. That was measuring that lower piece of area there is negative, and the second piece of area here is positive. So we know the lower piece is larger for sure, because he outweighs the positive piece. But the question is, what if I measure both of those areas as positive to get the distance traveled? Big thing here is that the split occurs at 3. All right, that's really what we're after. The split is going to occur at 3. So I'll consider this as the integral from 1 to 3 of v of t dt with a negative out front, because this part is already negative and I need to make it positive, plus the integral from 3 to 4 of v of t dt. And that one I leave alone because v of t is positive on the interval 3 to 4. I can put in what we're doing here. So our function is t squared minus t minus 6. And same deal here, 3 to 4. T squared minus t minus 6. Antiderivative step is not exciting. It's the same thing. 1/3 t cubed minus 1/2 t squared minus 6t evaluated from 1 to 3 plus same antiderivative 1/3 t cubed minus 1/2 t squared minus 6t evaluated from 3 to 4. Continue this down here. At the upper bound, negative bracket. 3 cubed is 27. So this is 27 thirds. Minus 3 squared is 9. So 9 halves. Minus 6 times 3 is 18. Minus what we have at the lower bound, which is 1/3 minus 1/2 minus 6. So there's the first bracket. And I have to add to that what I get by evaluating this at 4 and 3. So that's 4 cubed is 64 thirds again. Minus 4 squared is 16 halves. Minus 4 times 6 is 24. And from that we subtract 27 thirds minus 9 halves minus 18. Just barely enough space. Okay. The order you want to work in to clean this shit up is up to you. Probably what I would do, I'll distribute this negative, and then I think I'm going to have 2 copies of this thing. Yeah, here and here. Well, and I guess 27 thirds, we should go ahead and write that as 9. Minus 18. This negative will come here and make this plus 1/3 minus 1/2 minus 6. The brackets all go away. I've got 64 thirds minus 8 minus 24 minus same deal 27 thirds. That's 9 minus 9 halves minus 15. And no more brackets. Okay. This thing and this thing are identical. They have the same sign, so I've got 2 copies of those. This is minus 2, 9 minus 9 halves minus 18. And then these we just got to deal with. The 1/3 and 64 thirds. This time we can make 65 thirds, which would be still not an integer. Is there anything nice that I can clean up? Not really. So 1/3 plus 64 thirds, 65 thirds. Minus 1/2, minus 6, minus 8, minus 24. So negative 8 minus 24 is negative 32, minus 6 is negative 38. So I've got minus 1/2 minus 38. And what can we do from there? Tell you what, let's sort out the integers here, put that together for 38. So 2 times 9 is 18. This is negative 18. Negative 2 times negative 9 halves is plus 9. Negative 2 times negative 18 is positive 36. And then the other shit's still chilling. All right, let's just crunch it out. So negative 18 and positive 9. That's negative 9. Negative 38 and positive 36. That's negative 2. And then 65 thirds minus 1/2. Let's see. So 65 thirds. If I multiply this by 2 over 2, I get 130 over 6 minus 3 over 6. So I've got negative 11 plus 127 over 6. And let's see, is this divisible as 3 plus 7 is 10? This is not divisible by 6. So there's really not much else we can do besides take this and write it as negative 66 over 6, and then 127 minus 66 is something I'm too lazy to do in my head, so let's ask Desmos. 61 over 6. All right, just a little bit more than 10 meters, right? 10 and 1/6 meters. 10.16 repeating meters.
A question like this should always end up positive, right?
Yes. Distance traveled necessarily will be positive. Yes. The idea is whatever portion of this area that the regular integral would measure as negative, we are fixing to make it positive. So everything here will come out positive. You get a negative distance, call Einstein, complain. Or check your work. Probably check your work first, right? Yeah, let's stick with that. Okay. Any questions on the net change theorem or distance versus displacement? Or how to calculate integrals of absolute values? A fun story while we're here. When I was in graduate school, I studied analysis. That was my thing, right? Analytic number theory. So integrating absolute values of functions is bread and butter. When I first taught Calc 2, I put the following problem on an exam. First exam. The first Calc 2 test I wrote began with this. Less than half the class got it. Now you can unfold that. Of course, the easy way to do it is to think geometrically. This is a thing you can solve with areas really quickly. You don't even need FTC. But integrating absolute values shouldn't be all that hard. You just have to know really how the absolute value is defined algebraically, right? That definition we gave at the start of class. That will get you through any such problem. Okay. I want to talk for a minute about initial value problems. I always struggle to come at this from the way that most engineers think about it, but we'll but I can definitely give you a nice treatment of it from the perspective of a mathematician. These are problems where f primed of x is given along with one specific value of the function f. Like f of 0 equals 2. Something like that. This piece is called the initial value. Hence the name. And the idea is to find f of x. So let me give you an example. let's go with 2. Why not? Okay. I'll show you how to solve it, and then I'll show you a way to think about it that I find very useful. And certainly if you go on to take MAP2311 or any other course in differential equations, you will need to learn how to think of them in this way. F of x, we know, should be the integral or antiderivative of f primed of x. Which would be the integral of 1/3 x minus the square root of x. When we integrate x, we're going to get 1/2 x squared. So this is going to be 1/6 x squared minus the integral of x to the 1/2 is 2/3 x to the 3/2, and then you get a plus c. So f of x is some function like this. And to nail down specifically which function, right, this is really an infinite family of functions. For every possible constant c, you get a different curve. It's not all that different, but technically different functions. So we use this initial value to solve for c. Since f of 0 is equal to 2, we have f of 0 equals 1/6 times 0 squared minus 2/3 times 0 to the 3/2 plus c. And we know that that is 2. We know that f of 0 is 2. 1/6 times 0 squared is 0, minus 2/3 times 0 to the 3/2 is 0. And so you just get c equals 2. Therefore, the function f that solves the IVP is 1/6 x squared minus 2/3 x to the 3/2 plus 2. Problems of this sort are more deeply classified as first order linear IVPs. So you'll learn about the classification schemes later in differential equations. What I want you to do, though, is to think about what kind of information this is encoding. So we'll come to that in just a second. First, I guess questions on the solution procedure here. Any questions about how we came up with that boxed answer at the end? Okay, yeah, then let's return to the other question. This is encoding what kind of information? Think back to the start of the class. What did we use f prime to find?
Is it slope?
Yeah. So this tells us the slope of f at every x value in the domain. Let me compute a few of them. F primed of 0 is definitely 0. F primed of 1 would be 1/3 minus 1, which is negative 2/3. F primed of, let me jump to 4 to get to the next perfect square, would be 4/3 minus 2, which is 4/3 minus 6/3 is negative, what's that, negative 2/3 again? 4/3 minus 2. Yeah, it's 4/3 minus 6/3, again, negative 2/3. F prime I'll take the next perfect square of 9 would be 1/3 times 9 is 3 minus the square root of 9 is also 3, which is cute, that's 0. So what I can do with this is draw what's called a slope field. So I'll mark here, we've got 0, 1, 4, and we'll pretend like this is 9 over here. So since f prime of 0 is 0, I know that the tangent line, I can fill everywhere along the line x equals 0 with these little tangent segments that are horizontal. Since f prime of 1 is negative 2/3, I can fill the line x equals 1 with little tangent segments whose slopes are all negative 2/3. F prime of 4 also came out to negative 2/3, so I could fill all these with little tangent segments. That same slope. And f prime of 9 was 0. So I can put in a bunch of little tangent segments here. Like this. If we wanted to compute a few more of these, we can. Let me go ahead and do that just to get a more complete slope field, and then I'll show you what this is going to do for us. All right. So this is a little bit more negative. So f be like 3, 1, 2. Well, it's nice. Between 1 and 4, we've got 2 and 3. Looks like they're both pretty close there, but a little bit more steep on this side. And it's starting to come back. And then what else do we have? We'll do a few on the other side, like 6 and 8 maybe. So f prime 6 is negative 0.44, which is shallower. And then 8 was shallower still. So we'll say something very shallow, but negative sloped. That's the idea, is that giving the derivative allows me to fill out a slope field. And then when I tell you that f of 0 is 2, that lets me come in here and plop a point down. So f of 0 is 1, 2. And then I can draw a curve just by kind of following these tangent segments, like this. And that's the graph of the solution function. So initial value problems and a lot of differential equations can be thought of in this way. This is what's called, like I said, a first order differential equation, a first order initial value problem. And the goal always is to recover the function f. the sad truth is that solving differential equations in general is very, very hard. It's not something that human beings or even computers are all that good at, coming up with what are called analytic solutions. But by building a slope field and starting with a particular initial value, you can kind of imagine what a solution curve would have to look like. Yeah, it has to start off with a horizontal tangent over here, has to go down and then down steeper and then start coming back. And by the time we were over here, we had another horizontal tangent. Just for shits and giggles, let's see how we did, right? This sort of stuff is very qualitative. It's certainly not very precise, but if I graph this function, it should share some properties. Yeah, that's the idea, is that we get information about where we're increasing and decreasing, but even more quantitative, like how steep, how quickly we're increasing or decreasing at any particular x value. So the function that we got out as our solution was 1/6 x squared minus 2/3 x to the 3/2. Look at that, we didn't do bad at all. Oh, +2. There she is. So our guess was that this thing started off like this, went down, and then came back up. And the actual truth was it starts off like this, it goes down, it comes back up. If we had gone on to fill this out further to the right, we would have seen that f prime is positive and we start going back up. But if we restrict just to the, where do I go up to 9, let's say to 10, right? Like this, we actually did a great job. Not bad, right? So the idea of a slope field is a neat one. It's, I'll tell you, going to play, again, a big role in differential equations. And I think seeing it in the context of a first order initial value problem is a good thing. Basically, what this does is it tells you that it tells you kind of the infinite family of curves that you're talking about, right? This literally is what gives us this. And the set of all possible solutions would be this, with C being any possible real number, right? That's the idea. So for different values of C, right, these are all the sort of different curves that could fit that slope field. And then to pick out our particular one that was actually the solution to our IVP, it's sufficient to know the value of the function at one point. Okay. Let's take a look at one other setting where initial value problems show up. And that's physics again. Starting to get a little bright in here. So fix some lighting. So and this can be kind of multi-layered, involving a few integration steps. So looking for the word acceleration. Here we go. I'll find the velocity and distance traveled. All right, I'm going to modify this just a little bit. All right. So I'm told that an object moves along a straight path. Its acceleration is governed by this guy. This would be in like meters per second squared. His initial velocity is -4 meters per second, and his initial position is 2 meters. We want to find the velocity and position functions. So x of t is the position, which is the velocity, is v of t, and position is x of t. This would be what's called an order 2 initial value problem, because the acceleration, the thing that we were given explicitly, is the second derivative of the position function. So in the same way that integrating f prime should give you f, integrating a of t should give you v of t, because a is the derivative of v. So my velocity function is the antiderivative or integral of the acceleration function. The acceleration function is 2t plus 3. I'm going to leave off the units in the calculation here, so we need to clutter it. Again, just straight up power rule derivative stuff here, or antiderivative stuff here. I'm going to put a C1 there because we're going to do another integral, and we'll give them different names. So my velocity function, again, this prescribes a slope field. There are infinitely many curves that could fit that slope field. They're all of this form, t squared plus 3t plus some constant. To determine the specific constant that matches with this initial value, I can set -4 equal to 0 squared plus 3 times 0 plus C1. And this, of course, is the same as just saying -4 is equal to C1. So V of t is t squared plus 3t minus 4. So this is the velocity function, and I'm not happy with that part of the problem. And if I wanted to additionally recover the position function, I know that position should be the antiderivative of velocity. So it's the same thing, just now working with the velocity function that I found in the first part. And if you, again, power rule antiderivative here, we'd get 1/3 t cubed plus 3/2 t squared minus 4t, all right, plus C2. And I can use the fact that the initial position is 2 meters. X of 0 is 2. We have plugging 0 in for t here. I know that should be equal to 2, which is the same as saying that C2 is 2. So my position function is 1/3 t cubed plus 3/2 t squared minus 4t plus 2. It's not anything crazy. And we could proceed from v of t here to x of t down here. If I wasn't given the information to solve for C1, I could just leave it as C1. And here I'd have a C1 in my integral, and this would be minus C1 plus C1 times t plus C2. So when you have these, it's good habit to use different symbols for the different constants. Sometimes you will be asked to come up with the position function in general, leaving the arbitrary constants as arbitrary constants. But this is the general idea. This is the procedure. Integrate acceleration, that will give you velocity. Integrate a velocity, that will give you a position. When you're doing indefinite integrals, we can think of them as initial value problems. Any question on IVPs? All right, that really was everything I wanted to show you guys from section 5.4. We have covered this bitch pretty thoroughly. Are there any homework problems from the current set that you guys would like to look at? Anything that's been giving you a hard time? Go ahead and let me know in the chat. I'm going to refill my water here, and I'll look to see if there are. If there aren't any, then we'll go ahead and start to introduce the chain, backwards chain rule, U sub, and then we'll wrap up.
Are you talking about for this week's homework or last week's?
I was thinking this week's, but if you got stuff from last week's, we can do that too.
Well, number 4 from this week is giving me trouble.
I'm sorry, could you repeat that?
Number 4 from this week's homework has been giving me trouble.
Sure. Let me turn off the key. This will be more fun without it. Yeah. So a lot of these are more a matter of the algebra. Let's take a look. This is homework 12, number 4. We want to calculate the integral of the 4th root of x to the 5 dx. So the trick here is to remember the following algebra rules. If you have the nth root of something, that's the same as that thing to the 1 over nth power. And if you have something raised to a power, let's see, a, all raised to another power, those powers can multiply. So before I do any calculus here, what I would want to do is rewrite integral of 4th root of x to the 5 dx as the integral of x to the 5 all to the 1/4 power dx. And then using that second rule, this is the same as x to the 5 all to the 1/4. So that's the same as x to the 5 times 1/4, or x to the 5 over 4. And now we're ready to use our power rule. If I add 1 to this power, 5/4 plus 4/4 is 9/4. So I'll have x to the 9/4. And then I have to divide by 9/4, which is the same as multiplying by 4 over 9. So that would be my answer.
Thank you.
Yeah, of course. Anything else along these lines? The last couple homework sets that you guys would like to look at? Okay, then let me wrap up with a little discussion on what are called differentials. So this is a bit of like preliminary stuff that you're going to need to do the chain rule in reverse. You've heard me refer to the term dx, for example, here as the differential term in the integral. And that's correct. A differential is a little bit different from a derivative, but they're related to each other. The definition is like mind-numbingly simple. I'll write it like this. If u is equal to, say, g of x, then the differential of u written du is given by du equals g primed of x times dx. It's the same thing as saying du dx is equal to g prime, or like dy dx is equal to f prime. It's the same thing, just like multiply both sides by dx. The reason for the formality is dx and du, they're not numbers, they're something else. They're differentials. Geometrically speaking, they're objects called differential one forms that map a tangent space to a manifold down onto the real numbers. The way Newton and Leibniz and mathematicians who kind of first discovered this, they thought of dx as an infinitely small change in x and du as an infinitely small change in u. So what we're saying here is that if u is equal to g of x, then an infinitely small change in u corresponding to the infinitely small change in x can be calculated as the derivative of g times that infinitely small change in x. This is useful when one wants to change variables in an integral, and that's precisely what section 5.5 is all about. So for example, let's calculate the differentials. Okay, let's calculate du, where u is equal to e to the negative x. B. Let's calculate dz, where z is 2x. And let's calculate dw, where w is the inverse tangent of theta. Why not? It's a weird notation, but we'll do it. They're essentially derivative problems. You just have to write them in a slightly different notation. So du in this first guy should be the derivative of e to the negative x times dx. If I differentiate e to the negative x, that requires a little chain rule on its own. That's e to the negative x times the derivative of negative x, which is -1. So that's negative e to the negative x dx. Maybe a little easier, if z is equal to 2x, then dz would be the derivative of 2x, which is just 2 times dx. And if w is the inverse tangent of theta, then dw would be 1 over theta squared plus 1 d theta. Right, you really just take the derivative of the thing on the right and slap on a d, whatever the variable is, d theta, dx, whatever. You may remember that after we introduced the fundamental theorems of calculus, I gave you a few antiderivative problems that I said would be like kind of relatively easy. You can probably figure it out. A little bit harder. You might need to work on it for a while, and then like straight up impossible. I want to go ahead and reveal how to solve some of those. All right, now in general, I said give me e to the ax, right? I'm just going to demonstrate the method for you informally, and then on Monday of next week, we'll go over all of the formal stuff. The way this is done is by making a little substitution. So you're going to let u be 2x. And the idea is to turn this into an integral that's very easy to do. But we need to change, if we're going to change the variable here into e to the u, then I need to change the differential into a du. So I calculate the differential, which would be du equals 2 dx. And then from the du equals 2 dx term, I can say that 1/2 of du is dx. And then I go back to my integral and I replace all of the x stuff by u stuff. So the integral of e to the 2x dx would become integral of e to the u, because 2x is u. No longer would I have a dx here, though. I need to replace it with a du thing. Well, dx is 1/2 du. And that 1/2 is just multiplying everything inside this integral, so it can come out the front. And I'm left with the integral of e to the u du. Remember we said antiderivative is really best discussed in this notation. This is a big part of why. So I've changed the variable in the integral from x to u. If I gave you this integral on its own, never having told you it came from here, everybody could do it. You're just looking for an antiderivative for e to the u. Everybody could write that step down in isolation, whose derivative is e to the u, e to the u. And then finally, you go back to the original variable. And that's how the backwards chain rule works. If you were differentiating e to the 2x, you'd have e to the 2x times the derivative of 2x. Do you see how this is kind of reversing that? The derivative of that 2x is 2. And then when we replace this dx by 1/2 du, I'm undoing the like multiply by 2 that you get from the chain rule. So it's the work with the differential, the inner stuff, that allows this procedure to function as a backwards chain rule. I'll show you one more example and then we'll let you go. This one's more exciting because it's not just a matter of a weird constant somewhere. The idea is basically the same. If I wanted to differentiate the cosine of x squared, forget about the x up front for a minute. If I wanted to differentiate cosine of x squared, that would be a chain rule thing where the inner function is x squared. So let me make the substitution u equals x squared. The cool part is that the du here is 2x dx. And again, I'm going to divide over by the 2. I'm going to leave the x here, though. And I get 1/2 du is equal to x dx. And I'll just tuck all this in my little special substitution box. And then I'll rewrite this integral as the integral of the cosine of x squared times x dx. Just moving the x from the front to the back. It's all multiplication, of course, that's okay. And the magic is that x dx is 1/2 du. So this becomes the integral of cosine of x squared, well, x squared is u, times x dx, well, x dx is 1/2 du. The 1/2 can come out. And I have integral of cos u du. And we know that the antiderivative for cosine is sine. So this is 1/2 sine of u plus c. Finally, I know that u is x squared, so this is 1/2 sine of x squared plus c. And of course, we could check our work. If you ever want to check an integral, just take the derivative, d dx of 1/2 sine x squared plus c would be 1/2 times the derivative of sine x squared. Well, that's a chain rule thing, so that would be cos of x squared times the derivative of x squared, which is 2x, and the plus c differentiates to 0. The 2's cancel, and you get cos of x squared times x, which is the same as x cos of x squared. So yeah, it worked out. As powerful as the chain rule is for forward derivatives, this method, which is called substitution or sometimes u sub, even more powerful for antiderivatives. I'm going to show you multiple ways to think about this. And the way you should start is by thinking of it as a kind of backwards chain rule and looking at very simple examples like the ones I gave last week. On Monday, we will see many more examples kind of like this. And I'll give you some guidelines for figuring out when you can make a u sub and when it will work out, some warnings against when it won't work out, and how to tell if a u sub is going well. But this is sort of your first step on a long road of integration techniques, especially those of you going into Calc 2 next. You will learn many other tricks for calculating antiderivatives. And in general, they're hard. They're not anywhere near as easy as regular derivatives. But they're also a lot more fun. So the last little plug I'm going to offer here is for the math team. When I was an undergraduate, UF didn't really have any good math club. You know, there just wasn't something. So together with a friend of mine named Glenn Frost, we founded this thing called the University Math Society. And one of the events that I'm proud to say they have continued doing is like a spelling bee, but for integrals. So we call it an integration bee. It started at MIT, and it was something that I really liked and wanted to see come to UF. This is obviously an old website, but they did it just this last year as well. Let's see if I can find general. I don't know where the fuck they've got this shit these days. Anyway, there's a spelling bee, but for integrals, held at UF every year called the Integration Bee. And you'd be surprised just how far down the rabbit hole you can go with these things. There are some pretty fascinating integrals out there. Oh, they're still using this too. This is mine as well. Anyway, over the next few months of your mathematical lives, you will learn how to calculate lots and lots of integrals, some of them quite complicated, requiring very clever thinking. And this is the first little bit of that clever thinking. So on Monday, I will show you a lot more about u sub. Don't worry about it too much for now. Just wanted to get you ready. You do need to know how to calculate differentials. So your homework next week is going to consist of lots of differential calculation and a handful of easy use subproblems. And then we're going to talk about areas between curves. And that will be the end of content for the course. Everybody wanted to do the test on the 20th, which is fine, which means the 22nd will be a day of review for the final. So be mindful that your exam 3 is approaching quite quickly. Is there anything you guys would like to ask me before I end the meeting? Alrighty, then I'll go ahead and stop it here. I hope you guys have a lovely weekend and I'll see you on Monday.